So thanks a lot to the organizers to inviting me here and give me the opportunity to talk. So there's a mixture of experts and non-experts from what I see. So, but I will still try to be elementary in the first talk. So the aim of my lecture series is to describe to introduce the so-called Grothendieck six functors formalism with a view towards the motivic homotopy theory. So maybe I'll give you a short plan. So the first there will be five courses, but maybe one or two parts. The first one will be on axioms, examples, and formulations. Here I'll give the conditions from which you can derive the six functors formalism. Second will be about constructibility and duality. In the sense that it will be made precise, and maybe the last talk will be on a survey of the state of the art on motives, motivic case of mixed motives, to be precise. Okay, so just to introduce my my talk, I'll start with a bit of history. Of course, you heard the name. All this is due to Grothendieck formalism, and maybe Grothendieck reading faisceau algébrique cohérent of Serre and trying to understand and generalize Serre duality. So maybe I will recall Serre duality. So here we take a K scheme. K in fact K is a field of characteristics 0, I guess, but which is projective and smooth. Then you can state Serre duality like that. You look at the cohomology, just to simplify, coherent cohomology of X, and you look at the dual in the sense of this is a K vector space. You look at the dual in the sense of K vector spaces. So this is nothing else than the Hom, say in the derived category of K vector spaces, or of F low star. Here starts Grothendieck of sheaf of ring OX, bracket N, and you dualize with, let's say, K seen as a space. So this is usually the functorial interpretation of cohomology in the derived category. Okay, now because F is projective, then Grothendieck remarked that this is F lower shriek of OX. Okay, and now Grothendieck interprets the first step of Serre duality as just an adjunction formula. So F lower shriek admits an adjoint, so you compute this time in the derived category of O(x), of OX modules, OX F upper shriek of, say, let's write OK just to, and here this is minus N. Okay, don't have much space, sorry. So now the duality occurs here because F is smooth. So you can write omega x for the so-called dualizing sheaf, which is just the nth exterior power of omega x. Okay, then you can compute explicitly this adjoint, and this is omega x over k shifted d times. So this is because F is smooth. And in the end, you get the cohomology, so d minus n of x with coefficient in the so-called dualizing sheaf. Okay, so d is the dimension of x, dimension of f. So assume x is connected, so the dimension is constant. Okay, so much of development of six functors formalism by Grothendieck was driven by the idea that you can make this, you can extend and generalize this. First thing is that you can assume that f is non-smooth. And so here you'll get, instead of having this computation, you'll get here an object which is called the dualizing object. Okay. And so maybe just to end up historical reference, an important paper here is, if you want to look at this, the beginning of the story is Grothendieck ICM talk in 1958, where he stated the programs of developing duality and so on, and starts the program. So then the six functor formalism, let's talk of the early development by Grothendieck. So let me take my notes here. So first it starts in publication, so for covariant sheaves. It was written down by Hartshorne in the book Residues and Dualities. So the book is published in 1966, and Hartshorne states that this comes from Grothendieck seminar in 1963 in the US. And then there's a very important part, which is the étal formalism for torsion étal sheaves. And of course, this is SGF4. It was published in 1972, somewhat late, but it's a seminar from 63, 64. Okay, so not long after this ICM announcement of Grothendieck. Okay, so what's inside? And of course, later there were much development. First, the theory of Mori-Iko-Saito on mixed Hodge modules, and then the motivic story, which I will tell in this talk. So, but let's speak about the main things to do in this formalism. So first, we want to construct a pair f upper shriek, f lower shriek, f upper shriek, as in this blackboard here, of exceptional functor. And prove their many properties, which is these properties are what is called the Grothendieck six functor formalism. And then there is another part which concerns to establish, which is let's say the climax of this construction, is the duality statement. Sometime comes. So there are. This is slightly vague, and I will explain why, but this is usually called Grothendieck-Verdier duality. Or sometimes maybe there are other local duality, things like that. Okay, so this is why I insisted on this party. The choke is not good, but I like these little ones for the moment. Okay. So it's good that that Oliver has started this talk, because you will be accustomed to what will be. So now I will give a kind of very categorical part of the talk, which is about what you need to construct these functors here. So maybe just to finish the history, sorry, I should say that the story nowadays end up with the work of Vygotsky and most of all Ayub. So in motivic homotopy theory, there was for some time Vygotsky's cross-functor axiomatic, which was only available through notes of the line, but it was then realized the formalism was fully realized by Ayub. So let's say motivic 6 functors formalism and axiomatic of cross functors. So this is Ayub in his thesis, so I guess it's 2004, and it's published in Asterisk slightly later. Okay, so today I will explain an evolution of a theory of Ayub, which also use the formalism of SGA4 and the ligne, but which reach the same conclusion and give you the six-functor formalism for the categories that we consider in motivic homotopy theory. Okay, so let's start. As I said, so I will use a kind of a formal approach to this. So we start by taking S a category of schemes which will be our base scheme. So usually it will be all Noetherian finite dimensional schemes. Sometimes you need to restrict this, you need to look at excellent schemes, and for motives another example is for motives you are sometimes forced to use category of K schemes where K is a field, especially in the integral case. And also these finiteness assumptions have been relaxed recently by Marco Iwa, so you can take quasi-coherent, quasi-separated schemes if you want. It's a kind of sport to extend this generality. Okay, so this will contain our base schemes, and I fix another category, another part. This will be a class of morphism P, which essentially, these functors F lower shriek, F upper shriek are not defined for all morphisms, and P will be a class of morphism for which you have a kind of approximation of these functors. So axiom for this class of morphism is that they are stable under some operations. So essentially composition, of course, and most of all, base change. Okay. So this means, maybe I'll state this. So this means that if I have T, S, X, Y, a Cartesian square, such that T, S, X are in S, the morphism P is in P, then we get that Y is in S and the map Q is in P. Okay, so that's what you expect. And here, so as I said, I want to encompass both this axiom, the axiom which leads to the étale case and the motivic one. So here the examples are this. P can be the open immersions. This will be the classical case. The étale morphisms. This will be the case of SGA4 or the smooth étale morphism, maybe of finite type. This is not in the motivic case, we will consider smooth morphism of finite type. But you can also consider all separated morphisms of finite type. The assumption separated is not, strangely, is not absolutely necessary. Okay. Okay, so let's start with first definition. So I'm sorry, in this talk there will be many axioms. I hope you will not be overwhelmed, but so what do you need to build this six-functor formalism? So first we need data. So this will be first things for all schemes, for all base schemes. We are given M of X, symmetric. All my categories will be symmetric, so I say it one time. Symmetric monoidal category. So tensor product is denoted tensor X, or sometimes just tensor. In the homotopical case, it's usually denoted by smash, but it's the same thing. And there's also a unit, which I denote unit object, like that. Also, for all morphisms y to x in S, we are giving a base change functor and f upper star from m of x to m of y, which is again symmetric monoidal. When I say monoidal, it means strong monoidal, right? Otherwise, I say weak monoidal if there's only a map. So we'll see that in a minute. And we ask for axioms that were not. So first of all, we ask that the identity of x upper star is isomorphic with the identity of m of x, and we also have for any composition for any composable morphisms, we have an isomorphism like that, FG upper star, natural isomorphism subject to coherent conditions, which I will not write here. There's a co-cycle condition for this and something for compatibility here. And in rigorous terms, this means that all this can be summarized in the fact that there exists M from S to the two categories of, say, small monoidal categories, pseudo functor. So this is the which is contravariant on the one arrow. Okay, so this is, if you want the precise language, this is what you will use. So pseudo functors were introduced by Grothendieck. There's also a notion of a fibered category, which is a pendant of this theory here. But okay. What?
So the last row.
So this is equivalent to all this. Yeah.
Frédéric, I'm just wondering if we can make it a chain and functor.
That's right. That was my remark, and I was forgetting it. So there's an abstract theorem. I'm not sure who's the author, maybe Benabou and others, which says that whenever you have a pseudo functor with some isomorphism like that, you can find an isomorphic pseudo functor such that here you have equality. So there's a strictification theorem here. But so you will see that we have several. So yeah, in some sense you can always assume that there are equalities. But in a minute I will introduce other natural isomorphisms or transformation, and this you cannot assume that they are identities. So it's natural to do that. Okay. So now we start with some properties. So you see in Oliver talk, the functor f upper star between sheaves already has this property. It's constructed by left-can extension, so a priori you only have an isomorphism. Then when you derive it and you induce it on the homotopy category, there will be again an isomorphism, a natural isomorphism. So each time you can turn them into identities, but it's not so useful. I will explain now why. So now we have some properties of this data. And these are existence of adjoints, functors. So first we require that tensor product and f upper star admits right adjoints internal Hom, so I usually write it like that, and f lower star like that. So this is just a property. In other words, so for tensor product it means that the category is closed, symmetric monoidal closed, and these properties are automatic in the category of sheaves. So for f lower star, for example, like at first f lower star is given, and the theorem is that there exists left adjoint f upper star. But okay, we'll see example in a minute. And the last one is that if f equal p is a p morphism, say I will say sometimes p morphisms, because if p is a category of smooth, is a class of smooth schemes, then we say smooth morphisms. So if f is equal to p, then p upper stars admits, as we have seen earlier, left adjoint p, which is denoted p lower sharp. So the remark is that the fact that we have a structure of pseudo-functor upper star and these adjunctance properties implies that f lower star and p lower sharp automatically defines covariant pseudo-functors. So okay. So we could m lower star, okay, m lower star, m low shriek from S to, but this time only to the category of, to the two categories of small categories. So because these f lower star and p lower sharp will not be strongly monoidal. Okay, and now comes maybe just a blackboard. Now comes the first axioms, say, and then I will go to examples.
This cut is not symmetric monoidal?
No. So yeah, actually you can get that p lower sharp and f lower star are weak monoidal, one on the left, the other one on the right, but not more. So there are two basic axioms that are always fulfilled in the example, and in particular in the example that Oliver has given us. And these are some exchange isomorphisms. So the first one is that we consider, yes, so I have it here. We consider a pullback square delta as above. Then you can define a natural transformation that I will denote like that, x delta sharp star. And so you start from q lower sharp t upper star, and you first apply the map from adjunction q sharp j star, which goes to p upper star p sharp. So yeah, I just write add for the unit map of an adjunction. So the adjunction is p lower sharp p upper star. Now you use the fact that you have here you have a two-functor structure. So this will be isomorphic to q sharp and q upper star f upper star p sharp. And then you end up with, say, the co-unit of the adjunction q sharp q star, and this goes f upper star p lower sharp. Okay, so this is a canonical natural transformation, and our first axiom is that this is an isomorphism. So for any square and this is called sometimes a p base change property. Okay. The other thing is that you consider now any map. Yeah.
F is the map x to S.
Sorry. Yeah. Yes. Fortunately, I do not change notations, but this is it. Okay, then the next axiom is that you take P from T to S P morphisms. You take M an object of M of T, N an object of M of S. Then you have another exchange transformations, which is denoted P sharp star tensor. To be descriptive, so we start with from P sharp M tensor P upper star of N. Okay. Now you apply a unit map from the adjunction P sharp P star. This goes P sharp P upper star. Okay, now you use the fact that P upper star is monoidal, so there is a natural isomorphism here. P sharp P upper star P sharp of M tensor N. And sorry for the last map, it will be here. Then you use the co-unit of the adjunction, and it ends in P sharp M tensor N. Okay. The axiom is that this map is an isomorphism for any P morphism and any object like that. Actually, it's a natural transformation of B functors in M in N. Exactly. So this is called the P projection formula. okay, when all these properties are satisfied, I will say that M is a P primotivic category. Say, just to define, M is a P primotivic category. Okay. So just a remark. At this time we are very formal. So M, it's interesting to note that M behaves like a cohomology theory. So tensor product is the product on a cohomology. Upper star is the fact that the cohomology is contravariant, and the existence of F lower star is something which will hold more or less automatically. The map P lower sharp corresponds to what we, especially in motivic homotopy theory, we call isomorphisms. Okay, and then P projection formula and P base change formula are the exact analog of what happens in a cohomology theory, say for example like Chow groups. Okay, so maybe I have exercise to begin with. So first exercise is to find another way to define this natural transformation, the exchange between lower sharp and upper star, and show it coincides with the definition here. Sorry. Okay, so you also can build many other exchange transformation using the same kind of tricks. So you can define, so I will be a bit sketchy, the exchange between lower star and upper star. So it goes from F upper star, P lower star to Q lower star, G upper star for square like that, but P is not assumed to be in P now. And show it is an iso if, so this is F belongs to P. Okay, you have other things that I will sometimes use. You can also exchange have a kind of projection formula or natural transformation like that. Is it? Sorry, so goes to F lower star, F upper star, N tensor M, and ask when it's an isomorphism. Okay. Maybe I'll also give you another one. Well, so this one we usually don't use any notation, but there's another exchange transformation. So from the internal on M F lower star of M, and it goes to F lower star internal on F upper star M N, and so on. So it's a kind of internal adjunction formula. The fact that, yeah, you recover the fact that F upper star is left adjoint to F lower star. Okay. So in this theory, so you see, for example, here when I ask you to prove that there's only one exchange transformation in the end, this theory is heavily driven by some principle which is not a theorem at the moment, but it should be. So, for example, you know that there's a famous theorem of Maclane in monoidal categories saying that all the isomorphism that you can get from using the associativity formula and the unit formula, or even commutativity formula in some symmetric monoidal category, are unique. So in this setting of say P primotivic category, there is the same thing for the exchange transformation, but it's at this time it's just a principle. So remark is that there is a kind of meta-coherence of exchange morphisms. So all morphisms which are constructed by this kind of procedure, so I've listed the main ones here, are in some sense unique. So the principle is like that. The composition of exchange morphisms and maybe structural isomorphisms of pseudo-functor say, so first, say such a thing is called more generally exchange. So I will say basic exchange morphisms. Such composition is called just an exchange morphism. And the meta principle is that exchange, or say like that, two exchange morphism between the same composition of functors coincide. So maybe an example just so that you can see what I mean exactly by that. So first example is, suppose you take two pullback squares like that, S, T, W, P, Q, F, G, H, P prime, Q prime. Then you'll have something like that. The exchange from the composition of square between sharp and star will be equal to exchange sharp star contour exchange delta sharp star. Okay, so actually this is isomorphic through natural isomorphism. You have to draw the commutative square and prove it. But this is the kind of statements that you have to prove all the time during this study of P primotivic categories, and I won't do it obviously here. But also there is a lack in the theory, so I think at some point we should be able to prove something, such an assertion like that, like in the theorem of Maclane. So in the theory of derivator, for example, this is much a question. There are some tentatives for doing that, but at this time it's not solved. So in the thesis of Ayub, there's a lot of coherence like that are proved in terms of two diagrams, so that makes huge pages. In the book I wrote with Denishar Sizinski, we do much less about these coherences. Okay, now it's time maybe for examples. Now that I have a big
addition for two squares.
Yes, sorry. And this is the composed square. Also, a funny remark is that this principle here appears a bit hidden in SGA4. In some of the talk of Artin, I think he asked, so the exchange was between lower star and upper star, and he says there are two ways to define these best change morphisms, and I don't know if they coincide. So in SGA4, maybe 17, Delin says, look, I have a solution, so the two coincide using fibered category. But in fact, what's hidden is this kind of principle here. So it's not so easy. Okay. So we have seen an example in Oliver's talks. So the point is that there are plenty of examples. So maybe the first one, so is the category of sheaves of sets. I will say it like Oliver Stock. And actually you can check that these two the P-based change isomorphism and the P projection formula are valid even in the category of sheaves of sets. Here, because I have a view towards motives, I will state abelian examples. So what do I mean by abelians? So the settings is like that. You look at some category of sheaves. So first you can look at the pseudo-functors with two S maps to a category of sheaves of Zariski's sheaves on the Zariski site of S with coefficient in any ring R. R is any commutative ring. Okay. Then in this case, P is a class of open immersions. And what we have denoted J low sharp is what people usually denote G low shriek, like that. Its existence is formal. So then you also have take a topology T, so which I will state afterwards, and you look at the small étal site of R of S, so made by all étal schemes of S, or you can take étal schemes of finite type if you want. Then T usually in motivic theory is Zariski, so not always Nisnevich or étal. And then in this case, P is the category, well, no. Wow, okay. Then P is the category of étal, the class of étal morphisms. If you want, so here if T is Et, then you are in the situation of SGA4 and R is torsion ring. Then in this case, again, if F is étal, then F lower sharp is what you denote usually F low shriek, which is actually even defined in case of, say, SGA4. Even you can define this if F is quasi-finite, but it's not very important. And finally, what's most important for us, you can take category sheaves for topology on the site of smooth schemes over S of finite type, coefficient R. So all these categories are abelian monoidal. here T is the same thing, but P is the class of smooth morphisms. And that time you don't have such an interpretation of the lower sharp. Okay, the last example, which is interesting, which is not often considered, is that you can take the sheaves for the topology T on the category of all schemes of finite type over R. So topology can be these ones, but more interesting topologies are the CDH and H topology. And obviously in this case, as you see, the class P is given by morphisms of finite type. But in this case, you won't be able to get the full 6 functors, but I will tell something why it's interesting to look at this big category. Okay, so in this talk, this is what we look at. And you can see that in all these examples, you get some functor M. So maybe, yeah, into the category of abelian monoidal, even I should say Grothendieck abelian category. So these categories have all infinite coproducts. Okay. But so what for category of motives? Then we will start to derive these categories. And so the other class of example is the case, triangulated case. So these times M will be a functor. Yeah, I should put an up to the category of monoidal triangulated category. Beware that this means more than for abelian category. Sometimes you also have infinite sums. Well, all the examples that I will tell will have infinite coproducts. Okay, so they are, because we want infinite coproduct, these are all given by so to S you associate a derived category of sheaves on T on, say it like that, P of S, where T is one of the above topology. And P is one of the above class of morphisms. So, yeah. As you have guessed, the existence of a P lower sharp comes from the fact that the morphism of P belongs to the underlying site. So maybe.
Just one question. If we change topology, say from Nisnevich to Ital in the derived situation, to become clearly recalments of triangulated categories. Say if we pass from Nisnevich to Ital on the level of derived categories.
So if you use small sites here and here, you'll have gluing, but you are anticipating much gluing will be for the third talk. But and if you are with these sites here, you will not have gluing. Without using using a localization of this category stabilization. So yeah, so maybe we are anticipating. In the case of SGA4, so we use small site here. So these categories are already well behaved. You need, in case of SGA4, you need to take R to be a torsion ring with torsion prime invertible in the base scheme S. Okay. In the motivic category, you won't have gluing at this time, and you need the one localization and so on. Okay, but just fundamentally, nevertheless, these triangulated categories are in fact P satisfy all the axioms that I have described before. So what?
Substitute. So triangulated.
Here, this means that usually the triangulated categories admits all infinite coproducts. It's not so. In this example, this is why we don't take any bonds. If we take minus, plus, or b, then we won't have infinite direct sums. Infinite direct sums are used to derive functors. So maybe a kind of theorem is that this is P motivic category. So to do that, you need to derive all the structural functors, f lower star, f upper star, and the p lower sharp. So maybe yeah. So I have. So you need to go through an intermediate step in order to define this structure here, and this is the model category case. So in this time, again, the functor M will go from S to the two categories of model categories without just bare model categories with price. So monoidal model categories. So they admit any colimits and limits in my sense. And in this case, what we have is maybe I'm not sure I have time. In this case, you take the category of complex of sheaves on T, P, R, S, R. So on the category of complexes, this is just another kind of Grothendieck-Abelian category. You will have all the structural morphisms, and you want to define a model structure, and it's a T local model structure. Of course, you require that functors are equivalent left functors. Should have said that. So they are derivable. So there exists a T local model structure. So we have defined that with Cieszynski and myself, but this is all Cieszynski. And just to describe it rapidly, cofibrations or cofibrant objects are given by representable sheaves or SXT. So you take the three sheaves of our module represented by X, and you take the associated T sheaves, and X over S belongs to P. Fibrant object maybe that's more serious. Are given by complexes which so-called satisfies T descent. So what does it mean? Complex K is fibrant, so complex of sheaves is fibrant if, say, for all X, S in P over S, so the structural map of X over S is in P, for all T hypercover, you ask that the map from K of X to the total complex for product of K of a simplicial sheaf X is a quasi-isomorphism. Okay. This is equivalent to ask that the T cohomology of X with coefficient in K is computed as the T cohomology of the underlying presheaf. Am I going too fast? Maybe. Okay, but so this is documented then in a paper written by Sinski and myself called Grothendieck abelian categories and so on. And weak equivalencies, of course, will just be quasi-isomorphism. The interest of this model structure is that now all the structural functors that exist on the level of complexes are left equivalent functors for the left adjoints, and so the F lower star, for example, will be a right equivalent functor. Tensor product also is derivable. Okay, so I'm slightly late. There is a fifth example that I don't want to discuss here. You can go to infinity, to monoidal infinity category. In the sense of Lurie. So all the language to be able to formulate the axiom that I've written here are defined in Lurie's books. The two, you need also to look at the book on monoidal categories. For example, there's an extensive discussion on fibered infinity category. And instead of using this model category approach here, you can start with a category of complexes of presheaves. This is a DG category. And so in particular, a monoidal infinity category, stable monoidal infinity category. And then you can show that you can localize this infinity category and preserve the existence of a structural morphism. This is more or less the approach that Oliver described today. Okay, so the conclusion of this series of examples is that we have lots of examples which satisfy the bare formalism, and then in the next talk I will try to introduce other axioms which are more geometrical and which are more difficult to get usually. Okay, thanks. Yeah, I think this is, I'm not sure, this is the complexes, the total complex for product, not sum.
For product?
Yeah, I think so. Not sure. I have not checked, but yeah.
So when we consider triangulate how is it called? Quasi to the category of triangulated categories, then we need to require existence of all direct summands, or of all direct sums, or all colimits.
You use the existence of colimits. So in triangulated category, colimits are more or less the same thing as direct sums. Because you don't have colimits in a triangulated category, you just have infinite direct sums usually. You have homotopy colimits, but and this amounts to the existence of infinite sums. So the existence of infinite sums is a corollary of the construction. Here, to be able, for example, to get this model category, I really use the fact that you have co-limits in the category, in the underlying category, to be able to define fibrant resolution or co-fibrant resolution, actually. Mm-hmm. So this is something which is used to derive functors. So you can also have another approach. If you are in a triangulated category with infinite sums, then there are, and if the category is so-called well-generated in the sense of Neumann, then you have a theorem which states the existence of right adjoint. So for example, you can use this approach to assume that you have f upper star, then if you are in these triangulated categories with infinite sums, you will automatically have the f lower star, the existence of f lower star. We will use also this kind of thing. So this infinite direct sums is used to get derived functors and things like that. So in SGF, for example, they use the D- category usually. Mm-hmm. And this forbids the existence of certain functors. So they have to assume strong, but they already assume finiteness condition of their complexes, constructibility, and also a third dimension finite hypothesis, which ensure that all the functors they need exist at the level of D-. But if we had used D without the minus and used proper model category, we could have bypassed that. After that, the preservation of finiteness condition is a real theorem that we will see in the end.
Are there some other questions? And the